just to start with a little bit of expectation management. I mean, there are some other great talks around, and no, I don't want to get rid of you. Definitely not. I'm happy that you're all here, but I just want to make sure that you get the most out of it. And so just briefly talking about what you have to expect in the next 45 minutes that you can decide, well, is that what I expected, or is that something else, and I'd rather go. And I'm not going to talk, so you won't see any code in here, and I'm not going to talk a lot about design patterns and all that stuff. I did other presentations about that. What I'm talking about today is when you try to implement resilient engineering, resilient software design in your company, what are the most typical obstacles, challenges that you will face? And only partially they are related really to the activities of designing or implementing code. Most of the challenges you will face outside of that, which is surprising and not surprising at the same time. That's what I'm going to talk about today. So I bundled 7 of these challenges basically, and we'll discuss each of them briefly. If you now feel like, well, that's not exactly what I expected, feel free. Now's your chance. Okay, having said that, this is the most boring slide. So Uwe Friedrichsen, blah, 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 codecentric, blah, blah, blah. I have to mention codecentric because otherwise I don't get paid. But for the rest, maybe the only interesting thing down there is the slide share link. So that's my slide share account. There you can download the slides in case that you're interested in them. And yeah, that should be enough of that. And if you have a question about that, just ask me and drop me a message at Twitter or whatever. Okay, so let's start with the topic. Resilient software design. I mean, you pick that up somewhere and you say, yeah, that's a cool thing. It makes a lot of sense. Let's implement it in our company. And you go back home to your company and say, yeah, I have to start all that. And of course, because it's so obvious that you need that, you expect that to be an easy job. So like sitting on the beach, cool breeze, drink in your hand, soft music, and everything should be fine. I mean, it's so obvious that we need that. But somehow, wow, it's a cold wind, not a cool breeze, and there are dark clouds coming in, and what the heck's going on there? And suddenly you feel like in the middle of a thunderstorm, still with your drink in your hand, shaking. What the heck was going on there? It's heck, of course. No swear words today. So what went wrong? And you have no idea. And, well, I can't say exactly what went wrong in your situation. There are a lot of things that can go wrong. But from what I've learned in the last years about implementing resilient software designs, there are a lot of things that can go wrong. And quite often we will be caught by surprise when we're doing that, because the challenges show up where we don't expect them quite often. And what I collected here in this presentation is some 7 of the typical pitfalls that I personally experienced, and I want to share them with you. Of course, I called them quests because challenges, that's more manager speak, and it sounds odd. Quest sounds cooler, doesn't it? Yeah. So let's stick to quests. And let's start with the first quest, which is, understanding the business case. Because, as software engineers, we don't like business cases, do we? Not really. I mean, that's what other people are doing usually. And unfortunately, this can kill us before we even do the first step. And so we have to briefly watch that one. I mean, you go to your manager and say, yeah, I want to do resilient software design. And then your manager comes back with the question, well, that sounds like a cool idea. How much money will we earn with that? And you stand there like, wow. And you're dead before you even took the first step. I mean, there's a reason why managers ask that. It's sort of a litmus test. Are they serious? But also they're responsible for making sure that your salary gets paid at the end of the month. So it's okay if they're thinking about money. You also will find that in disguise if you go to your product owner or product manager and you say, yeah, we have to implement that, and they ask, will it improve our velocity, which is asking for the business case in a disguise, something like that. Which is, again, okay, but it's the wrong question in that situation. And to be prepared for that, you have to understand resilience is not about making money. It's about not losing money, which is a completely different story. And so the reasoning, so if you ever get into a discussion like that, the reasoning here is my suggestion how to start that discussion. If you don't do it, you will face reduced system availability. And the reason for that is the non-deterministic behavior of distributed systems. Don't ever try to explain distributed systems to someone outside of IT. It's impossible. So this is the only place where you have to say, believe me, it's that way. It's proven, there's literature, you can read that up. So at least the effects of that. And this will happen. I will talk about that in a minute in more detail. And if the system's not available, the users cannot do what they intend to do, which on the one side, you have an immediately lost revenue. So you lose money because they are not able to do whatever you want to do, which is the obvious one. And the other one is a little bit more subtle, but sometimes even more daunting. It's users get annoyed if that happens over and over again, and they will leave your company, turn to your competitor. The churn rate goes up in marketing speech. And so that's a delayed lost revenue cost. And so whenever you have a discussion about the business case of resilient software design, here's mostly the storyline. I cannot guarantee you that you convince your manager. It's still a lot of discussion and knowing how to talk to them and so on. And maybe they'll just stop out and say, well, that's all nice, but at the moment we have a different problem, and hopefully all will go well. So this ostrich strategy and so on, but that's a different story. At least you did your best, and hopefully you survived the first step. By the way, that's your resilience budget. These numbers. How can you come up with that number? Take your business monitoring. You don't have it implemented? Oops. Yeah, usually most companies don't have a business monitoring implemented. There you can easily see the revenue numbers and stuff like that. If you don't have that, start with some conservative estimations and try to get the buy-in from the other side. I mean, all business case discussions that I've seen, they were never decided here, they were always decided there. Business cases are decided in the gut, in the end. So this thing that we need, which is a strange thing for us software engineers, because we usually try to decide with our brains, but usually all these decisions are made by the gut. So pretend to address the brain, but actually address the gut. So try to get the buy-in. Find the numbers where they say, yeah, well, that makes sense to me. Ah, yeah, now we're talking. Okay, enough about that. You survived your first step, and you might face your second quest. And that's distributed systems. By the way, that's one of the hardest quests. So everything you basically need to know about distributed systems in a nutshell, Werner Vogel summarized in one phrase, which is that. That's all you need to know about distributed systems, basically. And it's very, very hard to cope with that. So from what I've seen, I deal with distributed systems for 25 years now, and I think I start to understand them halfway. So it's really hard to really grasp them and get these ideas in the brain and respond to that. And from what I've seen, more than 99% of all IT people haven't understood it really. So they think they do, but they don't. And why don't they really understand that? And why are they so often addressing distributed system actually in the wrong way? I think it has to do a lot with our education in IT and the way our brain is wired. Here's what I mean with that. What we learned in our IT education is basically something like, if X, then Y. Deterministic behavior. If I do this, this will happen, period. Guaranteed 100%. And everything we learn in IT and everything we build on is built on top of that deterministic behavior. So it's what I call inside process thinking. All our IT education is based on that, reasoning about deterministic behavior. It's designing a complicated system. The good thing is our brain is wired that way, so we can easily reason about that. It feels good to reason in deterministic passes. This will happen guaranteed. The problem with probabilistic systems is it's a little bit different. If X, then maybe Y. So there's a probability in here. And we all hated statistics, didn't we? Except for the machine learning people, but I'm not sure if they really like statistics or they just pretend to like statistics to get rid of us. I never understood that, but well, it's so hard to get the head wrapped around that. And this actually, in terms of design, that changes everything. So this is a cross-process thinking, how I call that, and that's non-deterministic behavior, because there are these probabilities in. Often it happens, but sometimes it doesn't happen, or it just partially happens, or terrible. And you have to reason about that and try to get a design right that takes that into account. And our brains are not wired for that, so we're really poor at that. Still, because we're used too much to thinking in that way, we use the left side thinking to design or solve problems on the right side. And, well, that leads to strange effects. Sorry. So what I see then is quite strange effects. And we see that all the time because when we go through the history of the distributed system and distributed system frameworks, DCE, CODEber, SOA, EJB, DCOM, and all that stuff, always were designed in a way that said, well, yeah, there's a distributed system out there, but we'll cover that behind interfaces, and you can think about the systems in the way over there. And it always led to brittle systems, which didn't scale and everything like that, catastrophe in production. So in a small scale, yeah, it sort of worked. In a bigger scale, it never worked. Because in distributed systems, you have failure modes, which you don't see in local systems. These are the failure modes, so doesn't respond at all. Sometimes responds, sometimes doesn't respond. Responds slow, the arch enemy of distributed systems, really hard, latency. Gives you the wrong response. Think eventual consistency and all that other stuff, orders and all that stuff, and message ordering, and Byzantine failure, so yeah, system went back, amok. So you have no clue what's coming next, and so on. And this leads to a lot of effects. There are a lot of papers out there in computer science, which we often try to ignore that they exist, because it's really hard to accept all that stuff. That all things which are no-brainers in a local system, or a lot of things that are no-brainers in a local system, which we take for granted, become really hard or even impossible in distributed systems. I mean, one of my favorite papers here is from Nancy Lynch. Sees also the L in the FLP, impossibility result, if you ever heard about that one. That's her, and she also proved the cap theorem, actually. So it was just a theorem from Brewer, and Nancy Lynch proved it 4 years later, that it's true. And she wrote a paper, 100 impossibility proofs for distributed computing. 100 things that are no-brainers in local systems which don't work in distributed systems. And we really have to grasp these ideas and pick them up and accept them and deal with them. So my recommendation is, embrace this kind of thinking, no guarantees, just promises, likelihoods, and all that stuff. So this non-deterministic behavior regarding the completeness of execution. So if you ever get an answer, when you get an answer, if you get a partial answer or a distorted answer, all these things are going to happen in the system. Message ordering, very important. So yeah, before you get the money is withdrawn. Is your system able to handle this situation? Because just the message order was flipped. And all these kind of situations. And communication, timing, I already talked about latency, and all these failure modes. But to be honest, you won't be able to prepare for all of that in your design. It will just make your brain explode. And that's an awful view to look at exploded brains. So you only have to accept it will hit you at the application level to a certain degree, and do not expect your infrastructure to hide all these effects from you. There are decent pieces of infrastructure out there which help you to get it a little bit easier, so even if you use an Istio or something like that. But infrastructure can only give you some kind of generic response behavior to certain situations, but your application sometimes needs this kind of behavior and sometimes that behavior. So it still will affect you on the application level, and you have to deal with that. And the least you should do is have a plan to detect if something went wrong and recover from that. So if you will figure out after 8 weeks, oops, my database went inconsistent because I missed a failure mode, have a plan how to bring that database back into a consistent mode. That's the least you should have. it sometimes really saves your lower back in production. But as I said, it's a hard one. Distributed systems are hard. They're really hard. I mean, from what I've seen in 35 years in IT, there are only two hard domains in IT, and the one is security and the other one is a distributed system. Everything else compared to that is peanuts, from what I've learned. And they're already quite hard things outside security and distributed systems. But they're really hard. But okay, maybe too hard for the moment to survive, so let's leave that quest aside. Say, yeah, we'll come back there later, but maybe solve an easier quest first. That's the 100% available trap. We see that all the time. Here's version 1 of the 100% available trap. So it's related to the distributed systems principles, but it's the smaller version, the easier quest. So here, you go to a business owner, product manager, whomever, and say, yeah, well, how should that application respond if a technical failure, if this kind of technical failure is going to happen, if I can't reach my database, if something out there, if the other system is down, if I don't get the right answer in time, and all that stuff. And then the business owner comes back to you and say, yeah, well, this must not happen. It's your responsibility to make sure that this will never happen. Well, yes, he fell for the 100% available trap. But it's not only the business side, it's also the IT people. This is a situation from a real project that I've been in, and where I just reviewed the design a little bit. And then I found a customer-facing service talking to a non-customer-facing service. And I just asked the developers, so yeah, well, how do you handle that situation if that non-customer-facing service is down, and how do you respond to that from that customer-facing service? Because you want to give back a response to the customer, so, or if it's just latent and stuff like that. And then, well, first developer said, no, we didn't implement anything extra because that non-customer-facing service is so important if that's down. So yeah, it's so important, and therefore it always needs to be up. 100% available trap. This assumption that everything outside of your area of implementation is always there, that the whole environment always is up. And developer 2 added, actually, yeah, well, if that service is down, we are not able to give any useful response anyway, so yeah, we didn't care. So we need that to be up, because otherwise we're not able to do anything. By the way, I come back to that with quest number 5, because that's another issue. But just to make sure, to understand, asking if a failure will happen is the wrong question. The right question is only to ask when a failure will happen. Everything around you has availabilities. Availability smaller than 1, which means it's not the question if they will happen, if they will fail. They will fail, guaranteed. The only question is when, and usually that is your personal Black Friday on the company, when you make the money of your life, when all the customers are buying like hell. That's usually when it happens. You can decide to handle that up front or then. I recommend to handle that up front, by the way. And just to understand that a little bit better, especially in the days of microservices and all that, which is a cool thing, but it comes at a price, as all things. Assume that one of your systems, your services, has an uptime of 99.5%, including planned downtimes. In an on-premise data center, nobody gives you such a number in their SLAs. Yeah, some host developers and say, yeah, we give you 99.7, and say, well, while your transaction monitors are up, and they're up from 7 in the morning to 8 in the evening, yes. Well, so your availability actually is 55%. Well, it's easy to guarantee 99.7 if you have a maintenance window of 11 hours. But, okay, and if 10 services are involved in giving a response to an external request, the overall availability is down to 95%. And if 50 services are involved, you're down to about 75%. So every 4th transaction average will fail. So 100% availability of everything around don't start with that, or otherwise you will be hit by these numbers. But again, that's easier to communicate, a lot easier to survive that quest than the distributed system quest. But okay, we handled that one, we survived the business case. Yeah, we sort of dealt with the distributed systems and the 100% available trap. What's next? The next thing that will haunt you is the ops dev feedback loop. I deliberately didn't write DevOps because that term, unfortunately, is broken beyond repair. Because go to in a room with 10 people and you get about 15 opinions what it is, and usually 18 of them are wrong. And so, well, therefore I turned that around. What do I mean with that? What you still see in a lot of companies is that big wall between dev and ops. So sometimes up to the C-level management or something like that. You're not allowed to talk just through the wall. Even if there's a window, you're not allowed to open that. Or core communication should go like that. Okay, if you have a candy bar or something like that, you might open the window and slip that through and so on. But not in an official way. Yeah. And this division of labor approach that we see there, it has some value if you only think about cost efficiency. But it comes at a price, again. And the price you will especially see in this domain if you really need to go fast, if you really need to create a distributed system landscape, which you usually have these days. The problem is, in a distributed environment, yeah, well, you cannot handle availability only on the infrastructure level. I mean, in the past it was developers, you care for the new stuff. Ops, you care for making sure that everything's up and running. And as long as the system only runs locally and doesn't have any connections to the outside except for batch connections, that's okay, because then your single most important issue is if the infrastructure is still alive, if your server is up, if your hard disks aren't broken, and so on. And you can care about all that stuff solely on the infrastructure level. But as I said before, in a distributed system landscape, all these effects will hit you at the application level, this non-deterministic behavior of distributed systems. And so you need to deal with that at least partially on the development level, on the application level. And so usually what you're trying to do is you try to implement a continuous improvement cycle, which is like, we have some problems that we've seen here in ops with your application. Oh dear, here's the figures, and well, yeah, oh, that's interesting. I haven't thought about that one. Yeah, let's implement some kind of response to that, some kind of resilient design in our application. And here's what I built to make it better. And then they run it and they give you back the number and say, well, it just worked partially. Oh, well, I missed that part. Let's improve that one, and so on. And it's a continuous improvement cycle. The problem with the wall is obvious. The cycle is broken. I mean, here is where you implement the measures, and here's where they take effect, and where you can see how well they worked. The wall is in between. Feedback cycle is broken. So, and even worse, even if you're a really motivated software engineer, which you all are, obviously, you're shooting in the dark. You have no idea if the stuff that you just implemented works or not, because you don't get the feedback. So, basically, the key observation here is, if you really want to implement resilient software design in your company, you need to have a working feedback loop. Otherwise, you don't need to start with that. I mean, it's nice if you implement a circuit breaker here or there or something like that, or some timeout management or some caches and so on, but you will never figure out if it made sense or it was just additional complexity in your code that nobody cares about, which is quite demotivating, by the way. And if you're then also just incentivized for completing more features per time unit because you have to improve your velocity because you're agile. By the way, it hasn't to do anything with agile. That's just cost efficiency in a disguise. Agile is something different. Then you will stop that quite soon. So you need to establish the feedback loop, basically. DevOps. DevOps is a cool thing, but again, actual real DevOps is a huge thing. So it will go into the organization, into the processes, into the way you create software, deliver software, the way you design software, everything. It will affect everything, the way you operate that, and. And therefore, sometimes it's a little bit too much for some organizations, so they rather like to adopt the ideas from Google, the site reliability engineering ideas, which is a little bit smaller, just with this focus of balancing innovation speed versus production availability, robustness, which is a nice thing. Or if you have a better way, implement it that way, but implement that feedback loop. Okay, feedback loop implemented, check, survived the quest. Number 5, that's again a daunting one. Mastering functional design. I mean, in IT, yeah, we're discussing this topic for more than 50 years, and we still are really bad at that, aren't we? And in distributed systems, this got an extra twist. My claim is, without a proper functional design, nothing else matters. So you can implement the best resilience measures that you are aware of on the technical level. If the functional design is not good, you will end up with a brittle system landscape, which will always be a little bit flaky and so on, and will not scale well and all that stuff. Why is that? Yeah, if we think about resilient software design, the core idea of resilient software design is isolation. Isolation basically means system must not fail as a whole, and to make sure that it doesn't fail as a whole, I split it up in parts, and I isolate these parts against each other so that a failure here doesn't cascade to other parts of the system. And in this way, I create a more robust system. So even if one part falls down, the other ones are still alive. Everybody says, yeah, well, makes a lot of sense. Yeah, let's do that. And bulkhead pattern is then usually what you see to implement that. And yeah, but the last line here is a little bit strange then. So, why is it saying that shaping good bulkheads, it's extremely hard? I mean, you might say, well, I do that all the time. I mean, I'm slicing and dicing functionality all the time in methods, in classes, across methods, across classes, across modules, across services, across whatever packages and so on. So why should that be hard? I say, well, how do you avoid this situation? Let's assume there's an external request which hits service A, and service A, to fulfill that request, needs a response for service B. That's what this response from the other developer, from the second developer, and the third quest was. So I need service B to be available to complete my request and give back a response. You've seen that, haven't you? Yeah, well, nodding. So, and due to the way the functionality is distributed between these two services, isolation is broken by default, because you can have a million circuit breakers in here. If this one is down, circuit breakers will only tell you, well, you're dead. Bad luck. So isolation is broken. Or how do you avoid that one? Here's an external request to some kind of functionality. Wow, that's no longer a microservice, that's rather a macro service, or even worse, because there's a lot of functionality in there. Let's split that up a little bit, and well, they're still a little bit big, so let's split that further up, and so on. And yeah, and now, yeah, that's sort of okay. And all of a sudden, you find yourself with a quite long activation path, so a lot of internal requests you need. And you remember this availability thing that I just showed you. So availability goes down with the number of involved services. Yeah, asynchronous behavior in some situations is okay, but only if you don't have to make an online response. So different story. So see that all very often. And then you struggle with that stuff in production and say, yeah, well, that doesn't work so well, so let's go back to that. And yeah, splitting up functionality in several pieces to implement isolation, well, it's broken. But you say, no, not that easy. Slow down over. So let's apply our well-known practices. We learned how to do that. Let's take computer science 101 here, divide and conquer, functional decomposition, we know how to do that. Or we're all craftspeople, craftsmen, craftswomen. So we apply dry, don't repeat yourself. We learned that for many years. We did so many katas and retreats where we trained that stuff. We are really great at that, and that's cool design. Or we are rather more like an architect, so we use more fancy terms as architects. So yeah, we do design for reusability. It's a holy grail in architecture, you know. And or layered design, which is another holy grail for the last 20 years or something like that. Or you might say, no, I'm smarter than that. I apply something like test-driven design or something like emergent architecture and so on, and say, well, these are cool techniques in a certain context, but in the end, you implicitly apply what you explicitly know. So you won't end up with a completely different design. It's just a different procedure how we come there, but you will use the same ideas again. The problem with all these ideas is this is designed for reusability and dry. That's a reusable service. And reusability, while having a lot of value in this context, shows its ugly head. And the ugly side of reusability is that it's the tightest coupling possible. So these are totally coupled, these two services. As soon as that's down, this one's gone. So, And of course, that's functional decomposition and layered design. And yeah, then while trying to fix the missing cohesion in here, we end up with that often again, and welcome to distributed hell. Everything we learned about design, usually in IT education and in our practice, is great inside a process boundary, but across process boundaries with that non-deterministic behavior, distributed systems, it doesn't help us. Some people then say, yeah, well, I still have caches. They will solve everything, so yeah, just implement a cache in here, and if that's down, I can still get the answer from the cache. And that's not a bad idea, basically, but also caches come at a price. So, well, the point is actually that if you don't care about your functional design and try to fix everything with caches, you will end up with a hell lot of caches. And you have to fill these caches, you have to transfer the data, you have to respond to the fact that they will be stale most of the time, so that they will be outdated, you will face different kind of inconsistencies which you have to deal with and so on. So you will simply end up in a different kind of hell if you just rely on caches. Again, caches are a cool thing in quite some places, but they are not a band-aid for a broken functional design. So basically my learning so far is we have to relearn how to do design right for distributed systems. And as we just have 45 minutes here, I have a few ideas which would be completely, are out of scope of that session. If you're interested in some of the ideas, I gave a talk at Kandinsky a few weeks ago here, and there is a recording which will be released then, and so Kandinsky 2018, and there I discuss some of the ideas and the findings I have about that topic. The only thing, the short version is no silver bullets, still out of stock. So it will be a hard topic, but we have to focus on how to get the functional design right, because otherwise, we have some kind of problems making these systems robust. Actually, we won't be able to make them robust if the functional design is wrong. Okay, that was a daunting one again. So let's look for an easier one. So we survived all these steps. Let's assume that we mostly survived that functional design. And now, yay, we finally are allowed to implement code. Yeah, that's cool, isn't it? I mean, all these things until we finally are allowed to really touch the keyboard. And then resilience patterns come into play. And there's also some danger involved that I've seen. So really understanding your toolbox. I mean, This is a picture of resilience pattern that I use in my workshop sometimes. And it's incomplete. And anti-patterns are missing and a lot more stuff and so on. But you see, there's a lot around there. So wow, which ones to pick and how many of them and how to combine them and so on. I started working on a pattern language, but as days unfortunately only have 24 hours and I have a lot of other things to do, it's still work in progress, so no solution from my side and haven't seen anything outside yet. And yeah, it's quite overwhelming and it has some strange effects sometimes if you see people picking up that stuff. So here, some recommendations about using these patterns. First of all, the most important thing from my point of view is patterns are options, not obligations. You do not need a pattern just because you know it. I mean, you might sometimes have seen these programs from people who just picked up a programming language, who tried to implement every feature of the language into that one program. They sucked, didn't they, these programs? I've seen that with Perl, which is an extra twist, because in Perl you can write completely, it was back in the 90s, and you can write completely incomprehensible programs that the originator, the author, doesn't understand anymore now, an hour after he wrote it or she wrote it. I've seen some of them, and also in other languages. Here's the same. So if you put too much into that, it becomes hard. And it's even worse here, because each pattern that you implement increases the complexity of your system. And complexity is the enemy of robustness. So if you really want to create something robust, it must be simple in some way. It must be easy to understand, easy to reason about and all that stuff. We need to find a sweet spot between, we need some patterns, but each pattern increases complexity, so we have to balance that. So no patterns are a bad idea, all patterns are a bad idea either, so we have to carefully balance that. And also, it costs money. Each pattern costs money in dev and ops. Usually, often redundancies involved in these patterns, which means extra hardware running at runtime and so on. And we have a limited budget, as we've seen. So in the end, we try to find a set of complementing patterns which address quite some situations usually. Just to give you a brief idea how other people did that, here, Erlang, basically, they are working with actor model and messaging, and what they use is they have this let it crash pattern, which is a combination of monitor, escalation, and restart, this worker supervisor thing that you also find in the Ecker library, which is basically a re-implementation of the Erlang principles in the JVM. That's how it started. Jonas Bonnet was just a little bit unhappy that his employer at that time didn't allow him to use Erlang. And so he had to go, well, if I can't use Erlang, then I re-implement it. That's how Ecker basically started. And they have a heart beating to see across Erlang virtual machines if they're still alive. And they have hot deployments, which is quite nice, because you have no downtimes if you deploy new code. And that's basically it. So these are the core patterns they implemented. And they were able to implement on Erlang telephony switches with an availability of 9 nines, 99.79%. So downtime, a few milliseconds per year, just with these few patterns as the basis. So you don't need 20 or 50. Or if we go to Netflix, for instance, they have a service-based design with request response, so HTTP-based actually most of the time. And due to the request response, they need more patterns to figure out if they get latency, so they have timeout circuit breakers and retry logic, bounded queues, and some stuff like that, and fallback. It's all baked into the Hystrix library that you might have seen. And then you also have redundancy of several times, especially for scaling up, so load sharing. They have a very decent monitoring. They have zero downtime deployments. They don't have hot deployments because it's on JVM, most of their stuff. But they use canary releases, they implemented them. And they have the famous Simian army, the error injection to make it sustainable. These days, we tend to call that chaos engineering, but that's basically the idea which is behind that. And so also a few more patterns, a different use case, but also quite limited stuff. And, well, they have a decent uptime, don't they? So they're quite reliable, especially if you have taken into account that sometimes they have about a third of the complete downstream traffic of the US inside the US. So they're quite big. They're running on more than 100,000 machines at peak times. And then the availability is quite impressive, I think. Okay. Now we implemented all of that. We survived all these quests. What's the last one? The last one is preserving what we've just learned. And that's a common pattern which is not specific to resilient software design, which mostly worries me across our whole domain. I mean, what I see, basically, I try to turn that into the Friedrichsen constant, this 5 years. And that's my personal observation. I see every 5 years, discussions about certain topics start from scratch as if there weren't any prior discussions. So last year, I attended a really nice unconference, but I decided then just to listen, which often is a good idea, by the way, but sometimes can be devastating. I just said, well, what are they talking about? There's a session about reusability. Just sit in there and listen to that. Maybe there's something interesting that I can learn. And I sat there and listened to them for 5 minutes, 10 minutes. I said, what's going on here? That sounds like 1968, 67, something like that. So nothing, as if nobody ever would have said anything about reusability, completely from the scratch, no knowledge, no prior knowledge, no nothing. I mean, everything you need to know about reusability was said in the 1970s. Just read the tar pit from Fred Brooks. There's 2 pages, and basically you can derive everything you need to know about reusability in this single paper, this single essay. And there are a few more things around there. Nothing there. And I worry, what's going on there? And I'm not sure, I'm not perfectly sure, but I think part of the story is the way we create insights and how we deal with that. So usually, the time we're working, we grow our knowledge. I mean, yeah, we also know people who are like that, or maybe even like that. But let's assume that most of us are constantly learning new things all the time. There's a difference, but there's a difference between knowledge and insights. So knowledge that stands the test of time. And this takes a bit longer because it takes you some time until you see some repeating patterns and so on. Say, yeah, well, that makes a lot of sense to keep that in mind, and that, yeah, let's better forget that stuff, and so on. And so this grows on a different rate. And this is actually nothing special for IT. That's something we see in all industries. But especially in IT, we have a very specific way to handle that. In other industries, if somebody is quite new in the domain and has a new problem, then what they tend to do is they try to look into the body of knowledge that exists for that engineering discipline or whatever discipline it is. We have a different strategy. We always look for the next silver bullet on the horizon. Well, I have a problem here, so maybe there's some serverless, microservice, Kafka resilient, CQRS, whatever solution out there that I can adopt. Would you ever look for a LAMP stack? Even if it would perfectly solve your problem? No, that's old stuff. That must be crap, of course. So, no, this is an old pattern. We can't use that. I mean, again, there's a lot of stuff I don't want to remember anymore. I'm happy that I can leave that behind. But there's also quite a lot of timeless wisdom in our domain, which we also tend to forget with this kind of youthism. So we also have this kind of technology youthism, which is very... So basically, what I've seen is we have to rediscover our insights every 5 years. I mean, there's a reason why Martin Fowler wrote a new version of his refactoring books and started basically from scratch, because there's so many people who don't remember that, the old book. Yeah, they started with JavaScript, so they will never read that other book, so let's write a JavaScript edition with that. Yeah, so, or to use it in a different way, we celebrate ourselves for forgetting everything that we've ever learned. which is a little bit hard. My problem with that, what worries me is, I'm not sure if how we really can become better with that. I have no perfect idea about that, or no solution. If you have a good idea, please share it, because my impression is we are not going to become an engineering discipline, a real engineering discipline, until we have solved that problem. And it's also irrelevant for resilient software design, because everything I've talked about and everything which I know about resilient software is nothing new. Quite some of the stuff is already there for 40 years or longer. So we just forget it over and over and over again. Wrapping up, 7 quests that you might face in your company if you try to implement that stuff. They're hard to do that. And the interesting thing is, most of those are only indirectly related to resilient software design, to doing that design and implementation part, which is surprising and not surprising at the same time, because we often figure that out after a while with new ideas, new concepts. The hardest one are probably picking up distributed systems, but that's a lot of time. And the next hardest one is probably mastering the functional design, where as a domain we are still quite bad. And distributed systems, as I said, add an extra twist for that. Learning the pattern is quite easy. And that's a question I cannot answer, actually. Well, that's what I had for you. And so first of all, thanks a lot for your time, and now I'm ready to answer questions.